Hello, my name is Kushalia Adhikari. I'm with the University of Rhode Island. The title of this work is Shift-Invariant Structure Imposed CNN for Direction of Arrival Estimation. This work is supported by the Office of Naval Research. The objective of this work is direction of arrival estimation. Consider that there are two signal sources, um, and these are propagating signals. We have an array of sensors in the far field of the sources. By processing the data received by the array, we'd like to evaluate the power at different directions. Then, the directions of highest powers are identified as signal directions. Our objective is to find these two angles, phi 1 and phi 2. Many methods exist for such estimation, and a predominant model-based signal processing method, which we'll use as a benchmark, is multiple signal classification. In this work, we'll use a data-driven method, convolutional neural network, instead of a model-based method. However, we will impose the signal model into the neural network. We'll demonstrate an efficient and accurate way to impose signal model into our neural network. We consider direction of arrival estimation as a classification problem. We discretize possible angles into 50 different classes. We feed the data collected by the sensor array to a CNN and find the probabilities of various classes or directions. The directions with the highest probabilities are our estimates. Now let's zoom into the hidden layers. The first hidden layer is a convolutional layer, which is implemented by filter 1. Filter 1 processes one segment of the input at a time and produces one neuron. By sliding this filter horizontally and vertically, we get a full slice of neurons. The filtered output then goes through ReLU rectified linear unit activation function. And similarly, we apply filter 2 independently to get another slice of neurons. Likewise, filters 3, 4, and 5 produce more slices of neurons, and all neurons go through ReLU activation. After the first convolution and activation, we apply max pooling to one depth slice at a time. The pooling function acts on a segment of depth slice 1 and produces just one neuron. And by sliding the pooling function horizontally and vertically, we get one complete slice of neurons, but with smaller dimensions. Similarly, we apply pooling functions to other depth slices independently, and we get more slices of neurons. That completes the first pooling layer. Next, we repeat convolution and activation. Filter 1 acts on partial length and partial width, but all depth at a time, and produces one slice of neurons. Filter 2 operates in a similar manner and results in another slice of neurons. The number of slices equals the number of individual filters, which in this figure is 5. All convolution outputs go through ReLU activation function. Then we apply second pooling function to each depth slice at a time. We then apply a third set of convolution and activation, followed by pooling layer. After that, we flatten the neurons to get one vector of neurons, which goes through a softmax function that will result in the output layer containing the probabilities of different classes. These are the hidden layers. Now let's see what we have for the input of the network. We compare 4 different input formulations in this research. And the first type of input we consider is the raw data, measurements made by the sensor array. Second, we find the scaled outer product of the raw data to evaluate the covariance matrix. This covariance matrix is expected to have all information that the data have. So we can use this as the network input. To find the third type of input, we have to perform the eigenvalue decomposition of the covariance matrix. The middle matrix here is a diagonal matrix containing the eigenvalues on its diagonal in the descending order of magnitude. The first two eigenvalues and the first two eigenvectors are associated with the signal, and the other eigenvalues and vectors are associated with just noise. So since the principal eigenvectors are related to the signals of interest, we use them as the CNN input. Before we talk about the fourth type of input, let's see how well these three input formulations work. This plot shows the CNN classification accuracy for the raw data at different signal to noise ratio, SNR. We consider filters of sizes 2 by 2, 4 by 4, 6 by 6, 8 by 8, and 10 by 10. What we can notice here is that the accuracy increases as we increase the filter size. Note that as we increase the filter size, the number of network parameters that we have to train also increases. So for the second input type, which is covariance matrix, the accuracy plot is shown in the second row. In this case, for a given filter size, the accuracy is higher than what can be achieved with raw data. So compared to raw data, covariance matrix as CNN input is more preferable. Now, if we look at the accuracy plot for the third input type, which is principal eigenvectors, what we notice is that even with filter 4, we achieve very high accuracy. So among three input types, principal eigenvectors is the best because they require the smallest filter size and consequently the least number of parameters that need to be trained. The principal eigenvectors capture the signal direction information pretty well. Now the question is, can we achieve further improvement? To answer that, we have to consider the structure that's present in our data and find the best way to enforce that structure into our CNN. So let's consider a sensor array with L different sensors. And there are two sources impinging on the array from angles phi 1 and phi 2. This information is embodied in a matrix called array manifold matrix, which we denote by A. This matrix is the basis of the two-dimensional signal subspace of the L-dimensional space. And if we consider all but the last sensor, then the corresponding manifold matrix will be all but the final row of A. We denote it by A bar. Similarly, if we consider all but the first sensor of this array, the corresponding manifold matrix is all but the first row of A, which we call A underlined. Our sensor array itself is shift invariant, and which means if we consider this blue box of sensors, it can be considered a shifted version of the red box of sensors. And it can also be viewed in a different way. If we consider the column span of A bar, it happens to be exactly equal to the column span of A underlined. And these two matrices, A bar and A underlined, are related by this matrix phi, which contains our signal direction information. So if we actually had the array manifold matrix, we will be able to evaluate the signal directions precisely. But in practice, we don't have access to array manifold matrix. But the shift invariant structure also appears in the data matrix. Suppose that there is no noise added to the signal and we have noise-free data matrix Y. And its singular value decomposition is as shown. The left singular vector matrix has been partitioned into two matrices U1 and U2. U1 contains the principal or dominant singular vectors. And this matrix U1 satisfies this relation. And if we knew U1, we would be able to compute psi, which is related to our signal direction. However, in practice, our data are noisy. So the singular vectors obtained from the noisy data matrix satisfy this relationship, from which we can estimate the psi matrix using an algorithm called esprit. But it is not going to be very accurate. Why? Because we know that array manifold matrix has a certain shift invariant structure, which is also present in the singular vectors of the noise-free data. But that structure is not quite present in the singular vectors of the noisy data, as shown here. An algorithm was developed in 2019 that finds a much better basis of the signal subspace using the singular vectors and singular values as shown here. And this basis X1 captures the shift invariant structure more accurately. Hence, we propose using the optimal signal subspace basis, the matrix X1, as the input to CNN. And doing so, we are taking advantage of the powerful data driven algorithm CNN, but we are also exploiting the structure in our signal model. Thus, we get the best of both worlds. And now in the fourth row, we plot the accuracies of the CNN that uses the optimal signal subspace as the CNN input. And what we see that is that even with filter order as low as 2 by 2, we get the highest achievable accuracy. And this shows that the optimal subspace captures the signal structure most efficiently and accurately. Next, we compare the accuracy of CNN with the classical method for direction of arrival estimation, music. In the top panel, we are considering a scenario with one source, and the blue line is for CNN trained with optimal subspace estimate, and the black line is for music. The accuracies are equal in medium and high SNR, but at low SNR, music is slightly better. In the bottom panel, we are considering a scenario with two sources, and in this case, the accuracy of the CNN trained with optimal subspace estimate is significantly higher. So to conclude, imposing the signal model and structure on CNN inputs, we can unify model-based DOA estimation algorithms and data-driven artificial neural networks. Optimal subspace estimates infuse the signal structure on CNNs more efficiently and accurately compared to other input formulations. Shift invariant structure imposed CNNs exhibit higher accuracy than the music algorithm. Thank you.